Morning, students. So today we are going to start our fourth unit, that is thin cylinder and thick cylinder. So first we should go for the topic of thin cylinder. So what is thin cylinder? That we are going to discuss. So first we should go for the topic of thin cylinder. So first we are going to discuss about thin cylinder. So what is thin cylinder? Where we are going to use that and all we are going to discuss, and how the way the stresses are developed in the thin cylinder, and what are the formula we are going to use to find out those stresses that we are going to discuss in the introduction part. So first of all, what is thin cylinder? So the vessels of wall thickness. The vessels are container how the wall thickness is less than that is the cylindrical vessel. Normally the cylindrical vessels of wall thickness is less than 1 by 15 to 1 by 20 of its internal diameter of its internal diameter. Then the cylindrical vessel is called thin cylinder. Okay, so here uh, so the cylindrical shape vessels which are going to uh, so the cylindrical shape vessel which are going to used for so like this we can have some cylindrical section. Okay, so here if uh, the wall thickness T should be less than 1 by 20, 15 to 1 by 20 of its internal diameter. So internal diameter we are going to take it as small d. Okay, of diameter means that type of cylinder we can call it as a thin cylinder. Okay, uh, so where we can use these thin cylinder? Where the thin cylinders are used? So in common practice, we are using, okay, now, such that boilers, okay, so boilers, maybe to carry, to store hot water or cold water, whatever it may be, or compressed air, okay, now. So these things are all we can boilers and compressed air receivers, compressed air receivers. So these and all the vessel used to store water or gas. So this is nothing but fluid. So fluid may be in the form of gas or water. Okay, no. So such kind of structure. Okay, no. Uh, under some pressure, under some pressure. Definitely, if I am going to store either water or gas in the container, okay, no. So it can exhibit some pressure in the wall. Okay, no. This is along the cross section and along the longitudinal section. So longitudinal section also I'm trying like this. Okay. So the pressure is acting at the inside of the wall of cylinder. Okay, now. So because of this pressure, it may exhibit some stresses. Okay, now. So that stresses only we are going to calculate. Okay. So this pressure will be uniform. Pressure will be uniform throughout its section or is uniform in the uniform throughout its cross section or wall. So this one we have to we are assuming that. Okay. So assume that the pressure will be uniform in the entire cross section of the wall. Okay. So this is the thing related to what is thin cylinder and where it is used. Okay. Now I said there are two pressure is acting. One is along the cross section and along the longitudinal section. So it have some name that what are all those uh, pressure that we are going to discuss now. And because of the pressure, how the failure is going to happen in the cylinder. That also we are going to discuss now. Okay. Now the thin cylinder vessel, thin cylinder vessel subjected to internal pressure. So as I already said, so so this is our cross section of the cylinder. This is thickness and this is the diameter. Okay. So along this, the pressure is going to act like this. So the pressure will be denoted by the letter small p. Okay, and if I'm going to take, if I'm going to consider the longitudinal section, so it is the closed container, so it can have the wall all around the section. Okay, so it is going to exhibit the, so this is the wall thickness T. This is the wall thickness T, and the pressure is going to act in the cross-sectional details along also in the longitudinal section. Okay, so the fluid under pressure denoted by the small letter P. Okay, so now small d is equal to internal diameter of thin cylinder. T is equal to thickness of the wall of the cylinder, and the pressure P is equal to internal pressure of the fluid. The fluid may be in the form of either gas or water. Okay, now next it have the length L. So L is equal to length of the cylinder. Okay, so because of there are two pressures are acting, one is in the circumference, another one is in the longitudinal direction. So because of that the failure is going to happen. So based on its direction it is acting now, the force will be separated into two different names. Okay, so because of this internal pressure the cylinder is going to split in longitudinal and in the cross section. Okay, so if I'm going to take the cylinder, okay, now so it's going to split up either like this, two parts, part one and part two. Okay, now that is along the length, okay, now along the cross section, or else it is going to separate like this. So this is half of the section and this is the half of the section like this. So this is along the length. So there are two types. So this is one and this is another two. So from the diagram itself, we understood if the stress or internal pressure is acting along the longitudinal, then it can have the failure. The that is the force is going to act. The pressure is going to act in the cylinder. Okay, now in the horizontal form. Okay, no, that is at the surface. It is like it is going to act here. Then it is going to get the failure along the cross section. Okay, and if the stress is going to act upside wall and the downside of the wall. Okay, now then it can split the entire section, that is along the length direction. So there are two types of failure is going to happen. Okay, so this is one, the forces due to pressure of fluid, due to pressure of fluid acting at the ends of the cylinder. Then it can tend to burst the cylinder like figure 1. Okay, and similarly the forces due to pressure, the forces due to pressure of the fluid acting vertically vertically upward and downward on the thin cylinders, on the thin cylinder. It's tend to burst, burst the cylinder like figure 2. Okay, so there are two types of failure. So one is it is acting on the sides so that the entire section, okay, that entire cylinder is going to divided into two different cylinders. Okay, now, and another one, it is going to have a two half of the cylinder like this. This failure can happen. Okay, now this failure is happen like this. Okay, now so that here the tension force is acting and here the tension force is acting, tension stress. Okay, now because of that it is going to have the failure like that, so that the force is acting these walls. Okay, and here in the cross section, okay, that is at the end. So if I'm going to consider this is cylinder now, so at the end of the wall it is going to act now, it is going to burst like a two different section. So this is one cylinder section and this is one cylinder section, like that it is going to get a failure. So here also we can have some uh, stresses. Okay, so this is the way the failure will be occur. Okay, so this, so if I'm going to take this is the longitudinal axis, the failure will be at perpendicular. Okay, now, and if I'm going to have consider the longitudinal axis to be here, the failure is in the plane along the longitudinal axis. So there are two types of failure. Okay, next, stresses in the thin cylinder vessel subjected to internal pressure. So stresses in a thin cylinder vessel subjected to internal pressure. So when a cylindrical vessel is subjected to internal fluid pressure, internal fluid pressure, the stresses, the stresses in the wall, the stresses in the wall of the cylinder on the cross section along the axis, on the cross section along the axis, comma, on the cross section perpendicular to the axis, are set up or taken place. Okay, now, so in the previous figure I said, okay, so here it is the going to divide the section into half of the portion. Okay, now, so here at the wall, the stresses is going to act. So this is nothing but one type of stress. And here the section is going to divide into two sides of circular section. Okay, now, and here also the stresses are going to act. So these stresses we are going to say. Okay, so the name as longitudinal stress or circumferential stress. Okay, so along the axis, so longitudinal stress. So if this is the cylindrical section, so the longitudinal stress will be developed here. Okay, along this. And the next one is circumferential stress or hoop stress. This stress will act along the cross section. Okay, so if the stress is acting along the cross section, then it will be circumferential stress or hoop stress. If the stress is along the length of the cylinder, then it will be called as longitudinal stress. Okay, the other name of the circumferential stress is nothing but hoop stress. So this is the thing related to our stresses. Okay, now next is expression for circumferential stress or hoop stress. Okay, so here I will draw the diagram so that so here, so this is my circular section. So I already said the stress is going to act in the cross section, that is called the circumferential stress. Okay, so because of these forces, okay, so because of this force, what will happen, the section may be divided into two halves. Okay, now that is top half of the portion, bottom half of the portion. Okay, now like this. So because of this stress, the if it is going to act like this, okay, the stress may, that is because the internal pressure is going to act like this, okay, now because of this pressure, the section is going to divide into two half of the section, okay, now along the longitudinal section, okay, now so this is called circumferential stress or hoop stress, okay, now so like this we can have our entire section. Okay, so now we are going to consider only half of the section. So if I am going to consider only half of the section, so here this is our wall thickness. So this is our wall thickness. Okay, so the forces is going to act here. That is internal pressure is going to act here. So that's why it is going to divide into two different half of the section along the length. So this is the length. So this is the length of the section L. So here wall thickness and the stress is going to act here. Okay, so this is our diameter D and this is our wall thickness T. Okay, now let us move on to the stress formula derivation. Okay, so first of all, consider a so whatever the statement, a small thin cylinder, we have to take it. It have the thickness of T and it have the length of L. Okay, and it is having the internal pressure small p. Okay, so let us P is equal to internal pressure of fluid small p, internal pressure of fluid, then small d is equal to internal diameter of the thin cylinder. T equal to wall thickness of thin cylinder. Okay, then sigma. So here the stress is acting now, that we are going to denote it by sigma 1. So sigma 1 is equal to circumferential stress, circumferential stress or hoop stress, circumferential stress or hoop stress of the material. Okay, now the bursting force will take place. Okay, if the force due to fluid pressure, okay, is more than, so bursting force will happen when the uh, force due to fluid pressure. The resisting force will happen when the force due to internal pressure will be more than the resisting force, more than the resisting force due to the circumferential stress. Okay. Meanwhile, if it under limiting case, under limiting case, okay, the force due to internal pressure will be equal to resisting force. Force due to internal pressure is equal to resisting force. So we all know that, okay, pressure is equal to force by area. Pressure is equal to force by area. Therefore, force due to fluid pressure, force due to fluid pressure, F is equal to pressure intensity multiplied with area. So where the pressure is acting? So pressure is acting along the circumference and throughout the length. Okay. So I'm going to take the area is equal to D multiplied with L. So this is the area so that the internal pressure will be acting, okay, along the diameter and throughout the length. So pressure P multiplied with D into L. So this is our force due to fluid pressure. So this is equation number 1. Next, force due to circumferential stress. Force due to circumferential stress. So we all know that stress is equal to load by area or force by area. Okay. So that load is equal to stress into area. Stress into area. Okay. So here circumferential stress we have denoted by the letter sigma 1. Okay. Sigma 1 into A. So sigma 1 into area in which sigma 1 is acting. Okay. So sigma 1 into where the area it is acting, sigma 1 along the thickness of the wall. Okay. And throughout the length. So L into T. Okay. And it have two wall thickness, either here one and here one. Okay. 1 and 2. So the area of which stress is acting on, so L into T plus L into T, such that 2LT, which is equal to 2 into sigma 1 into LT. Okay, now, so now I have to equate these two equations. 1 is equal to 2. So if I am going to equate this, pressure into D into L is equal to 2 into sigma 1 into L into T. So L gets cancelled. So that sigma 1 is equal to PD divided by 2 into T. So P is nothing but pressure intensity in the thin cylinder. D is equal to internal diameter of the thin cylinder. T is equal to wall thickness of a thin cylinder. So this is equation number 3. So if I need circumferential or hoop stress, then I have to go with the formula of sigma 1 is equal to pressure intensity into internal diameter divided by 2 times of wall thickness of the thin cylinder. Okay. Thank you.